Hello all, welcome to the hands-on series on Fundamentals of Generative AI and Large Language Models, Theory and Practice. In today's session, we'll be implementing the ensemble deep learning models. Ensembling in machine learning or deep learning has its own advantages. In case of ensembling, what we do is we take the predictions of different models, make the models run parallelly, take their prediction and either perform averaging of those predictions or then stack those one over the other and get the final prediction. In today's implementation, we are taking three different CNN models, that is convolutional neural networks, having its own customized way of predictions, and then we do the averaging of the predictions. So let us go through the implementation. As the usual procedure, we first import the necessary libraries. So importing TensorFlow as TF. TensorFlow is a deep learning framework which is required for building the neural networks. From tensorflow.keras, we import the datasets, layers as well as models. So importing of datasets is necessary because we are dealing with some of the datasets which are readily available either in UCI repository or Kaggle. So we are taking one such dataset, which is the CIFAR-10 dataset, which is Canadian Institute for Advanced Research dataset, having 10 different classes of data comprising of vehicle data, animal data and the bird data, which has 10 different classes. So we are importing one of such a dataset, then importing the different layers. So in order to build a convolutional neural network, we need a set of input layer, different hidden layers and the output layer. So all these could be built with the help of a function which is layers, and in order to construct or build or train the models, we need a function called as models. So for visualization purpose, we make use of the matplotlib.pyplot, which is in short called as PLT. Importing the numerical Python to deal with the arrays or numbers, we import it as NP. And from scikit-learn classification matrix, we import the confusion matrix as well as confusion matrix display. So this kind of matrix or a matrix display is required in order to show the performance of the model, wherein we try to compare the actual output with the predicted output of the model. So this is all about importing the necessary libraries. Next, coming to loading the data set. So we are making use of the CIFAR-10 data set. We load that data set into the training and the test set. So we have some portion of the training set and some portion of the test set. So we define two variables in each of this training as well as test. So xtrain, ytrain, which comprises of the input training and output training set, xtest and ytest, which comprises of the input test set and the output test set. So since we are dealing with images, and images has 256 different intensity values which can vary from 0 to 255. What happens to the model is it has to learn different values, maybe a smaller value which is 0, 1, 2, 3, and when we take on the higher side, on the brighter side of the image, it may have to learn up to 255 values. So in order to making the learning easier for the model, what we try to do is normalize the value. So normalize in the range maybe -1 to 1 or 0 to 1. So in order to do that, we take this kind of normalization, wherein we normalize the pixel values in the range 0 to 1. So we take all the pixel values, minimum pixel value will be 0. So 0 by 255, the minimum value is 0, once again normalized minimum value. The highest pixel value is 255. When we make 255 divided by 255, we get 1. So the intermediate values between 0 to 255 will anyways lie in the range 0 to 1. So we have seen this example in the previous session, wherein we try to build a CNN model, and we have seen with the help of example how we try to normalize the different pixel values. Now coming to the 10 different classes present in the CIFAR data set. The 10 different classes are aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship and the truck. So it comprises of various vehicle names, animals as well as birds. Now let us print the training and the test set. So xtrain shape and xtest shape. So shape is a function which will help in getting the length of the training as well as the test set. So in the output we can see that training data comprises of 50,000 training samples or the image samples, which are of the size 32 cross 32 cross 3. So the first 32 refers to the width of the image, next 32 refers to the height of the image, and 3 refers to the number of channels. So since it is a RGB image, there are 3 channels which refers to red, green and blue. Coming to the test data, there are 10,000 test samples. Once again, the size is 32 cross 32 cross 3, referring to the width, the height and the number of channels. Now coming to defining the different models. An ensemble model is a combination of n models, that is n could be 2 or more. So let us see with an example what is ensembling. So ensembling can happen serially or parallelly. In our implementation we are going for the parallel method. So we define one model, we call it as model 1. We define another model, we call it as model 2, and the third model which is called as model 3. We have training data, test data, both given to model 1, 2 as well as 3. So training data plus the test data. This combination is given to model 1 as well as 2 and the third model. So we have prediction 1, which is obtained for the first model, prediction 2 which is obtained for the second model, similarly prediction 3 obtained for the third model. Say we take index 0, say for example we want the prediction for index 0, that is we have X test and we have Y test. We want this for the 0th data. Now there is some prediction made by model 1. Say for example, model 1 predicts the 0th test data as truck, model 2 predicts it as same automobile class, and model 3 predicts it as truck. Then what happens is we have to take the majority of the classes. So two different models have taken the prediction, has made the prediction as truck. So the majority prediction is truck. So the final prediction will be truck. Final prediction will be truck. So what is the benefit of having 3 different models is we are making sure through every prediction that there is no major misclassification. But if you take model 1 alone, model 2 alone or model 3 alone, the number of misclassifications may be more. So what we are trying to do is we are trying to improve the performance by doing this kind of ensembling. So in case of model 1, we have used a customized CNN with some input layers, the convolution layers, max pooling layers and the dense layer. In case of model 2, we have once again we have used the customized CNN, but we have done this batch normalization. So batch normalization is a regularization technique which makes the model more generalized and tries to avoid the overfitting condition. And in model 3, once again it is a customized CNN itself, but we have used CNN along with the dropout concept. So dropout is one more way of regularizing the model, that is we are trying to reduce the number of neurons or effect or impact of certain neurons so that they will not memorize, one neuron will not memorize the contents or the images or the patterns of the other neurons. So with the help of dropout we are reducing the training, we are reducing the impact of certain neurons. So this is model 1, 2 and 3. So let us build these 3 models and let us see what are the predictions done by these 3 models and how exactly ensembling takes place here. So coming to defining the model 1, we are making use of the definition here, define or create a CNN1. So it is a sequential model because the layers are present sequentially one after the other. So we have the first convolution layers with the 32 different neurons or 32 different neurons here. 3 cross 3 filter, activation function is ReLU, input shape as mentioned earlier 32 cross 32 cross 3. So 32 width, 32 height and 3 channels. Soon after which we have the max pooling layer of the filter size 2 cross 2. So in the previous hands-on session, we have already seen the importance of this convolution as max pooling. But to summarize here, convolution helps in feature extraction. So as we go from the first layer to the second layer, the number of filter size has increased. So basic filtering happens with the help of 32 different filters. A basic filtering happens here, low level filtering, and deep extraction of features or high level extraction of features happens with 64 different filters. So this is where the model will be able to do the feature extraction and do some prediction for us. So this is about having two different layers of convolution. Now coming to the max pooling layer, whatever feature map we obtain from the convolution layer here or the convolution layer in the second case, that from that feature map we are trying to get the maximum values. So maximum values is nothing but the maximum pixel intensity that we are going to derive. So that refers to the that refers to the feature which is very much important, or the pixel which is highly contributing to the prediction or the classification. So that's why we are using the max pooling. And then we are having this image size. Image size is 32 cross 32 cross 3. We have 3 different channels here. So, and as well as it is a matrix of 32 width and 32 height. Now, this 32 cross 32 will be converted into 1D array with the help of this flatten function. Why this is required is, whatever feature map that we get after max pooling, that has to be converted, that is considered as features. Feature x1, x2, x3, so on up to the number of features that we get from the previous layer. So those features have to be multiplied by the weights and then added to the bias in order to get some raw score. From the raw score, we have to obtain the probability, and that probability will attribute or will correspond to the particular class, and that happens to the class label or the output label for the given input image. That is why we need to convert this 2D array or 3D array into a flattened layer, which is a 1D array, and at the output layer we have 128 neurons as which comprises the dense layer with the activation function ReLU, and finally one more output layer. Since we have 10 classes in our input data, this corresponds to 10 different neurons. So there should be 10 neurons because there are 10 classes in the given data. And final activation function is the softmax activation function, because we have more than 2 classes here. That's why we try to use softmax in order to get the probability as well. So this is the first CNN model that we have built. Now coming to the second CNN model, again a sequential model with the layers convolution layer, batch normalization, activation function used as ReLU, and max pooling. Similarly, the same combination repeated once again so that there is a high level filtering. So this is first convolution layer, this is the second convolution layer, followed by all the functions which have taken place in the first layer also. Batch normalization, activation and max pooling, followed by flattened layer which is used to convert 3D array into or 2D array into 1D array, and finally the output layer consisting of 128 neurons and finally the 10 neurons, because 10 neurons correspond to 10 different classes. Now the only difference between this convolution neural network when compared to model 1 is the use of this batch normalization. So what exactly is done in this batch normalization is, say we have the 2 cross 2 pooled output or the output from the ReLU activation function. Say if we have this, and this may be 2, this may be 10, this is 3 and this is 4. So for every value that is present or input value or the intensity value that is present, we find the normalized value. So x norm will be equal to the actual input minus the mean divided by the standard deviation. So if I have to find the value, normalized value for this 2, then this will be 2 minus the average of these 4 values, that is 2 plus 10 plus 3 plus 4 divided by the 4 values, and then the standard deviation. So this will help me in getting the normalized value. What is the benefit of normalized value is it will always lie in a particular range, and whenever we want a Gaussian kind of distributed data or a normally distributed data which follows the shape of a bell curve, most of the data lying within a certain standard deviation and very few outliers present, this kind of normalization is very much important. So when we have a normally distributed data, the outliers will be very much less, and because the outliers are less, the less number of misclassifications take place. So that is the benefit of having the batch normalization, so that we have a data in a proper range or a defined range. So this is the second model that we have defined. Now coming to the third model, once again sequential layer, because we have the convolution followed by max pooling, once again convolution followed by max pooling layer, and then the flattened layer with the dense layer. Now at the output side, what we try to do is this 128 neurons what we have are now deactivated. All the neurons will not be used. What we are trying to do is we are cutting short 50% of the neurons. See, we have hidden layers. Assume we have this kind of hidden layers. Every neuron can be connected to every other neuron in this way. So when it is connected to every other neuron, it is called as a fully connected network. So what happens is, if you consider this as hidden layer 1, this is hidden layer 2, and these neurons as A, B, C, D, E, F, always we know that we are going to get some data to D from the neuron A. Similarly, E will get from neuron A, F will get from neuron A. So when this kind of learning happens, all the neurons will try to memorize the data. So memorizing the data is nothing but memorizing the patterns. So when it tries to memorize the patterns only of the training data, in case of the unseen data or a validated data, it will not be able to understand the patterns. So this is where the majority of the misclassifications take place. So what we can do is, the same neurons if I take A, B, C, D, E, F, A we will try to give a connection to D, and from A we will try to give a connection to F. From B, let us give a connection to E, and B to D, maybe C to E and C to A. So with this, we are trying to reduce the connections or remove the connection from one neuron to another neuron, so that they don't memorize the data. So this condition is called as a dropout condition. Now out of 10 connections, if we remove exactly 5 connections, it is 50% of the connections which has been removed. So that is called as 50% dropping out of the connections. So what we are doing is, we are trying to cut off the 50% of the connection, so that we get a more generalized model. So this is all about the third CNN model, wherein we are trying to give importance to the dropouts. So we have defined 3 different CNN models. In the first one, it was just a customized CNN, a same CNN model which we had used in the previous hands-on. The second model, CNN with batch normalization, and the third model with CNN and dropout. So when we have these 3 models, let us build one ensemble model. So model 1, we have created CNN. In model 2, we have the second CNN. Model 3, we have the third CNN. So let us put together all 3 models in this way and compile that in a variable called as model. So we will try to use an optimizer called as Adam, loss as sparse categorical cross entropy. Why sparse? Because the 10 different classes are given 10 different unique integers. Maybe automobile may be called as a 0th index, truck may be called as first index, the car may be called as second index, and so on. So we have 10 different index varying from 0 to 9. Since they are integers, we are supposed to use the sparse categorical cross entropy. In case they are not integers and they have more than 2 classes, we can just use the categorical cross entropy. and if we have only two classes, we can be just adjusting it with the binary cross entropy. And now coming to the metrics, we can either measure accuracy or loss. So in this implementation, let us use the accuracy metrics. Now coming to training of the model. So we have three different models. So three different models have to be trained: model 1, model 2 and model 3. So training happens on the training data, which comprises of X train as well as Y train. Let the number of epochs be 5. We can always have more number of epochs. It is again based on user to user, how many epochs you want to use, how much time you can invest on learning as well as execution. So for simplicity, we have used only 5 epochs. And let the batch size be equal to 64. So we know that there are 50,000 training samples. Those training samples need not be used in a single stretch. Instead, what we can do is updation of the weights. Instead of happening at the end of 50,000 samples, we can divide the training samples into different batches. So first 64 samples we will take, we will do the prediction, we will find the loss. During the back propagation, we can find the weights. After updating that weights, that new weight is used for the next 64 samples. Again, do some kind of prediction, find the loss and updation of the weights. So that the second weight is passed on to the third one. So likewise, we have 64 different batch. We have the batch size as 64. And now let us divide this training data into validation as well. So let the 20% of the training data go into validation. That's why we have validation underscore split as 0.2. So the same thing is used for model 2 as well as model 3, because we have to train 3 different models. So now when we see the summary of this training, we have epoch 1 to 5 run for the first model. Again, we have epoch 1 to 5 which is run for the second model. Similarly, 1 to 5 run for the third model, because we have defined 3 different models. So at the end of 5th epoch, let us see what is the validation accuracy. So 67% is the validation accuracy for model 1. Then we see here 68% is a model validation accuracy for model 2, and for model 3 we have 61%. So batch normalization has really worked, or it is very effective compared to the other two models. So now coming to predictions. So averaging the predictions. So model 1 is used to predict on X test, model 2 used to predict the X test, similarly model 3 prediction done on the X test. So these predictions are saved in prediction 1, 2 as well as 3. Now that prediction we are considering here, taking the sum of it and then averaging, nothing but majority voting. So whichever votes are the highest, that particular class will be considered for the final prediction. So this is the ensemble prediction here. So this is saved, the ensemble prediction is saved in a variable called as ensemble underscore pred. Now ensemble underscore pred, likewise we will have 10 different probabilities because we have 10 different class. So whichever probability is the highest, we want the index of that particular probability. That index will correspond to the particular class, maybe automobile, truck, car, horse and so on. That's why we always mention argument maximum. So we want that index for which the probability is high, that has to be reflected. So that will be stored now in a new variable called as Y prediction. So this is Y prediction, which is got by ensemble of prediction. Now let us display the ensemble accuracy. So we define this particular function from metrics. So from scikit-learn metrics, let us import the accuracy score. So this accuracy score is got by obtaining the is got by comparing Y test as well as Y prediction. So let us save in a variable called as accuracy. When we try to print that accuracy with the print statement ensemble accuracy, we see that the accuracy is 71%, 0.7114. So which is higher when compared to the individual accuracy. We have seen that individual accuracy corresponded to 67%, 68 as well as 61%. So when we have done that for many number of epochs and for all the test samples, the ensemble accuracy is slightly higher, which is 0.71. Now coming to the last part, that is the confusion matrix. So in order to have a confusion matrix, we need to import the confusion matrix as well as confusion matrix display. So confusion matrix is a matrix wherein we try to compare the true label with the predicted label. So we want the Y test, which comprises of the actual label, and the Y pred, which comprises of the ensemble prediction done by 3 different models. So let us display the confusion matrix based on what is defined in this variable, that is CM. Let the color map be blue and let us show this confusion matrix. So what is happening in the matrix is, on the x-axis or on the rows we have the true label, and on the x is equal to 1 we have the predicted label, that is on the columns we have the predicted label. So we have 0th class, 1st, 2nd, 3rd, 4th, likewise up to 9th one, the index varying from 0 to 9, which constitutes the 10 different classes. Similarly 0 to 9, which comprises of 10 different classes. Unlike our previous hands-on, we have not shown the different classes here, the naming or the labels given here, just to make sure that it works even this way. Even it can work with the help of integers, and that is the reason we have used the sparse categorical cross entropy, because a model or the computer will not understand the naming or the label given. Instead, they will understand only the numbers or the integers associated with it. So now coming to the matrix here, whatever we see on the diagonal are the true classifications. That is, when 0th class is predicted as 0th class itself, then that kind of prediction, that kind of classification is shown here. So we have 805 such classifications when class number 1 is being predicted as class number 1 itself. Likewise, we have 839 such instances. Similarly, class 2 being predicted as class 2 itself, 547 such predictions. So diagonal elements are the correct classifications. Now coming to the non-diagonal elements, if I take this example of 19, class 0 being predicted as class 1. So likewise, we have 19 such examples. If I take example of 73 here, so class number 2 being predicted as class number 5. So we have 73 such examples. So whatever non-diagonal elements we have, when we sum it up, we get the number of misclassifications. So number of misclassification will tend to the loss that is given by the model. And the hues of blue are given here. Lesser the number, the lighter shade of blue, and the larger the number, we can see the darker blue here. So with the help of confusion matrix, it is very much evident that the number of correct classifications are higher than the number of misclassification, and that is why we have the prediction accuracy as 71%, which is more than 50% of the data. So in this implementation, we have seen the ensembling deep learning models. We have taken 3 different models, that is a customized convolutional neural network. The second model was customized CNN with the batch normalization technique, wherein batch normalization tries to have a normally distributed data which works on 0 mean and the standard deviation of 1. That is trying to give us the regularized model or a more generalized model. And the third model, we used a customized CNN with certain dropouts. So in this example, we have used 50% of the dropouts, that is 50% of the neurons were deactivated during training. So when these 3 models are made to run parallelly and only their predictions are being compared and average voting is being done, we have got the ensembled predicted output. So the ensemble predicted output or the accuracy was 71%, which is slightly higher when compared to the individual predictions. So we have seen the individual predictions as 61%, 67 or 68, which is less when compared to the ensembling model. So ensembling model will try to give the lesser number of misclassification, because we are trying to consider 2 or more models. for prediction. So this is where the performance of each of the models will increase, or performance of the ensemble model will increase. Thank you.